Hello, SWIC Earth Science students, and welcome to the next recorded lecture. This is looking at clouds, precipitation, and storms. So we're looking at two chapters. Chapter 17, which is moisture, clouds, and precipitation, and then Chapter 19, which is weather patterns and severe storms. Please do make sure you read the text this week. I am using a lot of material from previous classes. The textbook goes through a lot more terms than I'm going to go through. They also go through spend a lot of time talking about the different names for the different types of clouds. I'm not going to go through every single cloud type. There's no point in me basically reading definitions out loud to you. So we are going through two chapters. There are lots of terms. I'm not going to cover every single one. Just as a review, climate versus weather, or weather versus climate. So weather are going to be our short-term immediate conditions in the atmosphere. It constantly changes, whereas climate is going to be our long-term patterns. We are going to be looking at temperature and precipitation in seasonal variations across multiple years. Climate changes very slowly. So when we look at the daily variation in temperatures, that's weather. So if we have a record high, that's going to be weather. When we look at the average over an extended period of time, that average is the time of year temperatures over multiple years. That is climate. So water is extremely important for weather. So water, H2O, water is the liquid version. H2O is the compound. If it's solid, it's called ice. If it's liquid, it's called water. If it's gas, it's called water vapor. So I talked about this last week. When we go between these different phases, different states of matter, we will either have to absorb heat or release heat. So if we're going from a lower energy state to a higher energy state, that means we have to absorb heat. By absorbing heat, we make it colder around. I'm sorry. Yes, we make it. Did I say that right? Yes, you make it colder. You're pulling the heat from the surroundings. If we are going from a higher energy state to a lower energy state, we will be releasing heat. So we will make the surroundings warmer. So the process to go from solid to liquid is melting. We will absorb heat, so we make it colder by doing that. The process to go from liquid to solid is freezing. We will release heat. The process to go from liquid to gas is evaporation. We absorb heat, so it makes it cooler in the surrounding. This is where evaporative cooling works. That this is how when you sweat, why you get cooler when you sweat. And then if to go from gas to liquid is called condensation, and we release heat. We can actually go directly between gas and solid. We don't have to go through the liquid phase. To go straight from solid to gas is called sublimation. Note the amount of energy absorbed by sublimation is the sum of the two steps. So it is the sum of melting and evaporation. We're just doing it in one step. This happens actually often on glaciers, that ice will directly go into a gas state. This also happens with dry ice. Dry ice doesn't go through a liquid phase. Dry ice is solid carbon dioxide, and as it heats up, it goes to gas. And then the process to go from gas to solid is called deposition. Again, it's the same value as the two steps combined. This heat that is either absorbed or released by these phase changes helps drive weather as well. So clouds will form when water vapor, which warm air can hold more water vapor. Warm air also tends to want to rise because it's less dense than cold air. So when water vapor droplets will condense from the atmosphere, this happens when warm, moist air rises to colder temperatures that are in the higher parts of the troposphere. That colder temperature means that the air is not able to hold as much water, so its relative humidity goes up, and therefore it will start to condense out the water vapor into water. This will form clouds. So clouds are responsible for rain, snow, thunder, lightning, most of our weather phenomenon. Cumulus clouds are fair weather clouds. Cumulonimbus clouds are thunderstorm clouds. This chart shows us a bunch of the other types of clouds. Your textbook goes into a lot of detail. The high clouds are cirrus clouds. So if it's in layers or sheets, they're called cirrostratus. If they're poofy, they're cirronimbus. We can have anything that's sheeted will have stratus in it. Anything that's poofy will have cumulus in it. Nimbus or nimbo indicates rain. So nimbostratus are sheety rain clouds. Cumulonimbus are rainy cumulus clouds. So we have these different layers or different prefixes and suffixes indicating different types of clouds. Altus indicates the middle. There's not one for really, so the middle one are going to be called the alto. There's not really a prefix for high and low. And then we have the different names of the clouds. If they are wispy, they're called cirrus. If they're sheets or layers, they have stratus. If they're globally poofy, they're called cumulus. So we combine those different ones together. Your textbook describes every single one of these. I don't feel the need to. So clouds form by condensation. So this is the step that goes from water vapor to liquid water. So again, relative humidity is the amount of water in the air compared to the capacity the air has at that temperature. So it's a percentage. The closer we are to 100, the closer we are to full capacity. Dew point is the temperature when water vapor will condense. So if we're at the dew point, that means the water vapor can condense into water. Warm air holds more water than cold air. Warm air is less dense than cold air, therefore it will lift up. As it's rising to higher levels of the troposphere, the temperature will drop, so therefore the air will start to cool, which means that it is no longer able to hold as much water, so the relative humidity will increase because we still have the same amount of water as we had when it had a higher capacity. Now it doesn't have as high of capacity, so we will form clouds. Your textbook goes into very detailed descriptions talking about the different ways we create these instabilities and have the clouds moving, including the adiabat, which is the pressure gradients that and temperature temperature gradients, which will make air move up and down. So our weather processes are going to be primarily these differences in pressure and temperature. So atmospheric pressure, which I talked quite a bit about last week with the atmosphere, is important. Atmospheric pressure basically will cause air masses to move. So we're looking at the weight of the air column. Circulation patterns will be closely related to pressure. Circulation patterns are how the air moves around the globe. Vertical stability is whether or not individual packets of air will move up or down, so that's going to be closely related to the temperature. And Coriolis effect is the spin of the Earth, which is what's going to direct things. We don't see straight lines often. So these circulation patterns, warm air tends to mass at the equator, and this produces low pressure because warm air is less dense. That low pressure is going to want to pull more air into it. This warm air wants to convect upward because, again, it's less dense. So the warm air will have water in it. It will be moist, so that warm, moist air will convect upwards at the equator. As it's moving upwards, it will start to cool. Eventually, it will cool enough that the relative humidity increases, will form clouds, and eventually will drop precipitation. That is going to happen, at low latitudes, and so we will have rainforests where that happens. This air is now cold and dry and dense, and so it will start to sink. It sinks around 30 degrees, going towards both poles. So around 30 degrees, both north and south, we have an area of dry air descending, and therefore we have a lack of precipitation, so we tend to have deserts. So these are subtropical mid-latitude deserts. There's a similar pattern that happens centered around with the low pressure centers around 60 degrees. It's not as pronounced as what we see in the tropical regions because the temperature gradients aren't, or rather the amount of water available isn't as great. So it's not quite as pronounced, but we do see a similar pattern centered around 60 degrees as well. So this upper figure is showing us the globe with these air currents and these pressure centers. We're seeing those cells around the planet, and this lower figure is showing us a cross section at the equator. We have the cell happening. We have 30 degrees where again we kind of have the same thing going in both directions, and then we have one centered around 60 degrees as well. We also have circulation patterns that happen around the planet, not vertically. So these are jet streams. A jet stream occurs where you have air masses of different temperatures meeting. So these are in the northern hemisphere are westerlies. They flow from west to east, which controls much of our weather patterns. This is due to the Coriolis effect. The greater the difference in air mass temperatures, the faster the jet stream will flow. So there are two in the northern hemisphere. We have the polar jet stream that it resides at about 10 kilometers elevation, and the subtropical jet stream at about 13 kilometers elevation. The polar jet stream is much stronger because the difference in temperature between the Arctic and subtropical air is much greater than subtropical versus tropical air. So the peak flow is about 2 times the wind speed. They tend to be a couple hundred kilometers wide and several kilometers thick. The polar jet stream is significantly stronger because that boundary is more drastic. The polar jet stream is stronger in winter because we have a stronger temperature difference than we do in the summer, and we can see that here. Also, the polar jet stream pulls south in the winter because that cold air, the boundary between the cold and the warm air moves south as well. Severe weather locations are often controlled by shifts in the jet stream. So where we see the jet stream poking up, we call that a ridge. We tend to have high pressure associated there. Where it pulls down, we call that a trough. That's where we tend to have low pressure. Pressure centers are where we're having air flowing into or out of a region. Now, I admit this can be confusing to think about because we have air flowing in one direction and out the other direction because we're looking at a vertical column. When we say we have air flowing into or out of a region, we're actually talking about up in the atmosphere. So in areas where we have convergence, so we're having air flowing into the region, it will stack up and that will form, that air will pile up and it will become a high pressure region, which means as we get towards the surface, the air will want to move out. Where we have air flowing out of a region, that is going to decrease our air pressure because we are pulling things out. That means we will have low pressure, and so air will want to flow into that region at the surface. Okay, so we have both diverging and converging in each of these columns. These first 2 points are discussing this top part of our columns. So the combined temperature and air movement will produce low pressure centers, which are called L's or lows, and high pressure centers, which are called H's or highs. Everything in the earth goes from high to low. So we're going to move from the high pressure to the low pressure. The high pressure centers produce ridges in the jet stream. The low pressure centers produce troughs. So by looking at the jet stream, we can actually determine where these pressure centers are, which is quite important for our forecasting, weather forecasting. The Coriolis effect is where we have uneven distribution of solar radiation between the equator and the poles, so we get pressure and temperature gradients. Air does not follow a straight path. The Earth is rotating, and this is causing the deflection. This is what we mean by the Coriolis effect. So the Earth is rotating west to east. So this means that Earth is rotating counterclockwise. If you view from above the North Pole, it will appear opposite from the South Pole. So we are looking at this, looking at the North Pole, the Earth appears to be rotating counterclockwise. The Coriolis effect in the northern hemisphere deflects things to the left, to the right in the northern hemisphere, and it will deflect to the left in the southern hemisphere. So things don't go straight. So this is why we have this curved path to most everything. So cells produced by areas of high and low pressure will also follow the same pattern of deflection. This establishes predominant wind patterns that we see repeated over and over again in our weather. Vertical stability is the movement that is caused by vertical temperature differences in the air. So atmospheric stability refers to the tendency of a parcel of air to move or remain stationary. An air parcel is stable if it is in balance with the surrounding air, both temperature and density, and it doesn't want to move. It's unstable if it isn't in balance with the surrounding air, so it's a different density or different temperature, so it wants to move away to where it is stable. So commonly we see unstable parcels when light, warm, moist air is overlain by dense, cold, dry air. So that moist air wants to move up, the dense air wants to move down. Parcels will either sink or rise due to instability. So severe weather is associated with this instability. If we move air parcels around, we are going to basically have the ingredients for severe weather. Fronts are the boundaries between cool and warm air. So warm air is always going to rise over cool air. A cold front is where we have cold air moving into a mass of warm air. A warm front is where we have warm air moving into a mass of cold air. So the warmer air will always be lifted by the cold air, and this will form clouds, because remember, warm air is moist, and when we push it up to higher elevations, it cools down and then condenses into clouds. The water vapor condenses into clouds. The question is, how fast does that happen? If we are pushing cold air into a warm mass, we push that warm mass up very quickly. So we will form clouds very quickly and typically very violently. So cold fronts are typically associated with violent weather. Whereas warm fronts, where the warm air is moving into the cold air, the warm air will gradually rise. It's not being forced up quickly. And so this tends to be more fair weather, where you don't have severe weather associated with the warm fronts. A stationary front is where we don't have a lot of movement between our air masses. They're basically just sitting there. An occluded front is a special case where cold air overtakes cool air, and it will actually wedge warm air above the frontal boundary. So we get this wedge of warm air sitting above cool or cold and then cool air. They each have different symbols. You looked at this in lab the previous week. So an occluded front is going to be these purple symbols. Cold fronts are going to be these blue symbols. Warm fronts are going to be the red. And then we have both of those together. That's a stationary front. Thunderstorms happen everywhere, especially in equatorial regions. They need warm. Okay, they don't happen everywhere. They don't happen in the polar regions as much. They can happen across the globe, though. They need warm, humid air in the lower atmosphere. It's helpful to have a steep temperature gradient vertically so that the warm air will rise fast. And it's also helpful to have updraft, forcing the moist air to colder levels of the atmosphere. But the important thing is that warm, humid air that will rise up to colder temperatures. They are very common along cold fronts because that's where we're forcing that warm air up quickly. So what happens in a thunderstorm, our moist air is forced upwards. It will cool down. That moist air, no longer, as it cools, the relative humidity increases. So that will start to form our cumulus clouds. If moisture and updraft continue, the relative humidity continues to increase and the cloud will grow. The upward growth of the cumulus clouds are called the cumulus stage. The cumulus cloud will become a cumulonimbus cloud, a thunderstorm cloud, as we continue condensing clouds and we start releasing more and more of that latent heat from the water condensation. So we are actually going to be heating up. We're adding energy. So this cloud will start to dome and tower, and this will get bigger as the precipitation starts. So the precipitation is going to occur because water freezes into ice and snowflakes in the upper reaches. The larger snowflakes will fall because they will not be supported by the updrafts. As they move through warmer air that's lower in the cloud, they will melt. In the lower parts of the cloud, those liquid drops will collide with one another to become larger drops. Those larger drops will not be supported by the updrafts, and so they will fall as precipitation. The mature stage is when we have both updrafts pulling new moist air up into the upper parts of the clouds, but we also have downdrafts being pulled down by the falling precipitation. So this will continue to grow until it reaches the top of the unstable atmosphere, at which point the updrafts will build out into an anvil shape. So we're going to spread the cloud up at that level of unstable atmosphere. We have very heavy rain, lightning, thunder, and hail during this stage. The dissipating stage will be the final stage. This is when the upward supply of warm, moist air is starting to be shut off. It's being overcome by the downdrafts in the lower cloud. The downdrafts, as it starts to overwhelm the updraft of moist air, that upper air no longer will have moisture in it. So the downdrafts will start to pull some of that now dry, cool air down, which will cause some of the liquid in the lower cloud to evaporate. This will cool the cloud even more, which will further slow down the lift of warm, moist air. So basically, once the downdrafts overcome the updraft, the cloud will just run its course and run out of fuel to continue the thunderstorm. A storm is considered severe if it hits certain markers, so it has to have a high enough wind speed, if it produces large hailstones, or if it produces a tornado. Thunderstorms are pretty much self-perpetuating. As long as they have access to warm, moist air, they will keep going. Once that warm, moist air is shut off, then they will shut themselves down. So we have to have that warm, moist air, so we have to have a high water vapor content, having the updraft that pulls that warm, moist air up into the dry air mass above that is cold. And it's helpful to have changes in wind shear, or large vertical changes in wind shear. So wind shear is where we have different velocities and directions of wind as we go vertical. This is caused by an increase in wind velocity with altitude, not attitude. And so we change the horizontal direction of the wind with altitude. This leads to a rolling motion, which obviously can help pull up as an updraft. The greater the wind shear leads to greater thunderstorms. Are different types of severe thunderstorms. So we can have mesoscale convective systems, MCSs. So these are the most common. These are large clusters of self-propagating storms where the downdraft of one cell will lead to the formation of a new cell. So they basically propagate across a large region. These last for about half a day. We can have squall lines. These are a linear belt of thunderstorms that will develop parallel to a cold front but ahead of it. Squall lines are common actually out in the oceans as well. And then we can have supercells. These are the most damaging of our storms. This is where we can have mesocyclones. So we have a spiraling column of air. That's what we're seeing in this figure here. These are identifiable with Doppler radar. These are the ones we're typically looking at when we're looking at our severe weather on television. They are smaller than the other storms, but they're much more violent. These are very much capable of producing tornadoes because of that spiraling. There are other ways to get tornadoes too. Lightning is one of the characteristics of severe weather. So lightning is the flash of light that is produced by discharge of extreme volumes of electricity. It heats the air to an extreme temperature, 30,000 degrees. This causes the air to expand very rapidly and it creates a pressure wave. That is what we hear as thunder. So sound moves slower than light. Light moves at 3 times 10 to the 8th meters per second. Sound moves at 333 meters per second. So light moves much faster than sound. Also, the thunder comes after the light anyway. There are 2 types. We have cloud to cloud, which is starting and ending in the clouds. And then we have cloud to ground, which is the one most people are more concerned with. This is where it actually connects to the ground. So how does lightning occur? So in a cumulonimbus cloud, as it grows and we start to have warm, moist air reaching the upper parts of the cloud, it will start to develop ice pellets. So if that upper part of the cloud is cold enough, ice pellets will form. Those ice pellets will interact with each other and start to build up a charge. Like charges repel, so the positive charge in the top of the cloud tends to push the negative charge to the bottom of the cloud. The negative charge that concentrates in the bottom of the cloud will push away the negative charges in the ground below it, leaving a net positive charge. So the negative charge in the bottom of the cloud will be attracted to that net positive charge. So a line of electrons called a stepped leader will leave the cloud towards tall objects on the ground. A streamer of positive charge will also, from the tall objects on the ground, will be attracted to the negative charge in the bottom of the cloud and will reach towards the bottom of the cloud. This is called a streamer. So as the stepped leader approaches the streamer, a spark will attach to the leader and that completes a circuit. And then the return stroke is a surge of heated air, and this is what our lightning is. We get additional leaders and streamers following the same path, and that's why we get flickering of the lightning. So the lightning actually does start at the ground and goes up to the cloud. Hail is another symptom of a severe storm. So hail is when we have a hailstone is an individual large piece. So hail are concentric rings of ice that form in clouds. So basically what happens is that it will start off as an ice nucleus, and as it moves, it'll be ice when it's upwards in the cloud. If the updraft isn't able to support that ice, it will fall further down in the cloud, where it either will melt slightly into a liquid layer or collect liquid around it. If it gets caught back up in the updraft, it will then freeze again. And so it will move up and down within the cloud repeatedly to form these concentric rings. We can get hail any time of the year, really. What we need is this movement up and down within the cloud and the cold temperatures in the cloud that allow the ice to form. So you can get hail even when it's well above freezing at the ground surface. Tornadoes form due to vortexes. So we have to have a vortex extending down from the cloud, typically from one of these mesocyclones, to touch the ground. So this occurs where we have large differences in atmospheric pressure over short distances. Supercells are going to be the main spawner of tornadoes. So we have a wall cloud forming in the lower portion of the cloud due to updrafts. It will start to spin. So that's what we are seeing here. And that forms a funnel cloud. If that funnel cloud connects with the ground, it becomes a true tornado. Dust, debris, water vapor, and whatever else will get caught up in the funnel. That's what gives the tornado its color. Again, it's only a tornado when it's in contact with the ground. Wall clouds and mesocyclones are not necessary for tornado formation, but this is the most common way to form tornadoes. We can also have what are called suction vortices, which are smaller, intense whirls within a larger tornado, so they're basically like mini tornadoes. There are multiple stages to the tornado. So the mature stage is when the tornado is big and fat and fairly straight up and down. The shrinking stage is when the tornado starts to thin out and will start to tilt more. We have an increase in winds at this stage. And the final stage is the rope stage, which is the decaying stage. It is still very dangerous, potentially more dangerous because it's less predictable. Not that tornadoes are ever really truly predictable. Tornadoes come in a variety of sizes. They can be quite large. They come in a variety of wind speeds. How fast the winds are will determine the size and the size on the tornado scale. Tornadoes wind speeds are faster than hurricane wind speeds typically. They travel sometimes just a short distance, but they can travel for hundreds of kilometers. They move very fast on the ground. So tornadoes are very, very fast. They are faster. An EF5 is going to be faster, have higher wind speeds than a hurricane. An EF5 has incredible damage. I don't really need to talk about the damage to people that live in Illinois. You have seen the damage from tornadoes. You know what can happen. Excuse me. Sorry, had to sneeze. Luckily, I was able to pause it before I sneezed into the recording. Tornadoes can be extremely damaging. Even a small tornado is still very, very damaging. So tornadoes can occur everywhere. The US has more tornadoes than any other country. The Canada is second to the US. This is because of our weather, topography, and geographic location. We do have what's known as Tornado Alley and then Dixie Alley as well. Tornado Alley is that area where we have increase or the highest number of tornadoes. So this is looking at tornadoes throughout the year. The spring and summer months are the highest rate of tornadoes. So tornado days are days that are likely to spawn a tornado. There are varying estimates on where Tornado Alley is. Is it moving? Is it expanding? How wide is it? And there is also quite a few tornadoes down in Florida. I believe most of those have to do with hurricanes, though. But tornadoes can occur anywhere, technically. We do, I will show these images again of a tornado that hit northern Pennsylvania. I used to teach in Pennsylvania, so I like to bring it back to them. I don't have to talk about the different tornadoes that have hit in this area. Lambert Airport has been hit by a tornado at least once, I think twice actually. Poor Joplin has gotten hit many times. So in this area, we know about tornadoes. Most kids in Pennsylvania don't know about tornadoes. They don't do tornado drills in their schools. I asked my students that all the time in Philadelphia. What drills do you do? They would do typical fire drills. They never did tornado drills. They never did earthquake drills. Hurricanes, you don't really drill for that because you know it's coming. So it was a little bit fascinating. But this is a viaduct, a wrought iron viaduct that was just picked up and twisted around like a child's toy by a fairly low, I think it was an EF1 tornado. We have blizzards. We're going to learn later on today about namings of storms. These storms, which are called extratropical cyclones or mid-latitude cyclones, typically don't get named other than if they follow specific paths. So like the Alberta Clipper is one that follows this blue path. Nor'easters are ones that go up the eastern coast of the US. Typically these things don't get names. We're going to see the tropical cyclones get names. Severe weather during winter are called blizzards. So in the US you have to have a certain velocity of wind, you have to have a limited visibility and a duration. If we can't see anything, that's when we call it a whiteout. A ground blizzard is recirculating of previously fallen snow, which can be just as dangerous as the initial blizzard. These blizzards happen when we have interactions between low pressure troughs and surface low pressure systems. Low pressure all around. Blizzards have wind associated with them, which means we have to be concerned with a thing called wind chill. Wind chill is the temperature felt due to the moving of air. So air temperature is what is the actual temperature. Wind chill is what does it feel like. So if the wind's not blowing, I can tell you from experience, -30 doesn't feel that bad if there's no wind. The second you get any wind, it becomes miserable very fast. You have felt this as well. If you're walking around, there's no wind, you don't really notice it. The second that wind picks up, you start to really notice it. That's what wind chill is. It can be very, very dangerous. So in addition to just the snow and ice, we have dangers of frostbite. I don't really want to talk about frostbite, but I will explain frostbite if anyone wants to know. I encourage you not to Google frostbite pictures. You will be totally disturbed. But frostbite is basically your blood develops ice crystals and your skin or your tissues freeze. It happens to your extremities first. And this is, if you do experience this, you don't want to rub it because you don't want to burst your blood vessels. But people do lose extremities to frostbite all the time. Hypothermia is where your body starts to shut down non-vital systems to try to keep the vital systems running. And eventually those vital systems also shut down. So your body gets too cold, and to try to keep important things running, your functions start to slow down. And so hypothermia actually can help people survive falling into like freezing water. They go into hypothermia and it actually helps them survive longer because it shuts down their breathing so that their heart will keep beating and then they're not suffocating. Don't count on that, but it does happen. Both of these are very dangerous. Frostbite you can recognize in yourself. Oh, I can't feel my fingers anymore. That's not a good thing. Oh, look, they're purple. Hypothermia you tend not to recognize in yourself because the first symptoms are you're acting like you're drunk, you're very disoriented. So other people tend to recognize that in you. And then there's also accidents. You can imagine limited visibility, falling debris, great winds. This is going to cause accidents. Ice storms, I personally think, can be more dangerous. So an ice storm is where we have ice accumulating in large quantities. So it will accumulate on anything and everything, including power lines and tree branches. So you can have downed power lines, downed tree branches. Also, ice I describe as the great equalizer. I don't care how good you are at driving on the snow. No one is good at driving on ice. Ice will make an idiot of everybody. Also, no one is good at walking on ice. I don't care how good you are. You will fall on your butt at some point. Whether or not we have ice or snow is going to depend on the thickness of the mass of cold air at the surface. So if all of the air is cold, we'll have snow. You know, if the precipitation remains frozen all the way down, it's just going to be snow. If we have warm air all the way down, that's going to be rain. Both of those are good conditions. It's where it's in between that we can have problems. So if we have a thick layer of cold air, so if we have a layer of warm air that will melt our precipitation that is liquid, and then if it moves through a thick layer of cold air, it has a chance to refreeze and will fall as ice, and that is sleet, which is not as bad as the other condition. The other condition is called freezing rain. This is where that layer of cold air at the surface is very thin. So we have our precipitation will melt, that it will be liquid, but it's cold liquid. And then it will move through this thin layer of cold that will make it very, very cold. And the objects at the surface are going to be either at or slightly below freezing temperatures. So when that very, very cold liquid hits that very, very cold object, it will freeze instantaneously. So you basically coat everything in ice. And that is just the invitation for disaster. So this is what we see here, that if we have this thick layer of cold air, then we have a lot of time for our precipitation to turn back into either ice, which would be sleet, or it remains as snow. If we have a thin layer of air, we're basically going to super cool our raindrops, and so that material is then going to freeze instantaneously when it makes contact with cold objects. And that is problematic. All right, for the rest of today, I'm going to be talking about tropical cyclones and other cyclones. So this is a picture of Superstorm Sandy, which was the largest Atlantic hurricane on record. The diameter was 1,800 kilometers. Sandy was insane. So cyclones are areas or centers of low atmospheric pressure characterized by rotating wind. So we have low pressure centers with wind rotating around them. The Coriolis effect will impact how they rotate. So in the northern hemisphere, they rotate counterclockwise. In the southern hemisphere, they rotate clockwise. A tropical cyclone is between the tropics. It's between 5 and 20 degrees latitude. These are not associated with frontal boundaries. They have a warm central core. That warm core is what drives them. So they're driven by heat. Extratropical, or as your book calls them, mid-latitude cyclones, are outside the tropics, typically between 30 and 70 degrees latitude. These are associated with fronts, typically cold fronts. They will have a cool central core, so they are not going to be driven by heat. So cyclones are going to be characterized by the intensity. This is the sustained wind speed and the lowest atmospheric pressure. Tropical cyclones are extreme severe weather. So we have tropical depressions that turn into tropical storms that turn into the cyclones. We typically refer to them as hurricanes. They have different names depending on what water they form over. Extratropical cyclones are less severe weather. These are things like windstorms, regular thunderstorms, snowstorms, blizzards, etc. The difference between these two is that the tropical will derive their energy from warm ocean water. Warm ocean water is necessary. Once it loses contact with that warm ocean water, it will no longer be a tropical cyclone. Latent heat released during cloud formation also helps drive it, so we need heat. Warm air is the driver here. If they move over land or the water cools down, they will lose the energy source and dissipate, or they can become one of these extratropical cyclones. An extratropical cyclone, on the other hand, the energy is being derived from horizontal temperature contrast between air masses on either side of a front. So we're looking at these contrasting temperatures, so cold air here will be the driver. So they are both cyclones, they're spinning, but they're spinning for different reasons. There are special cyclones. So for example, a nor'easter is an extratropical cyclone that tracks northward along the eastern US and Canadian coasts. That's the only, well, we also have things like the Alberta Clippers. Most of the extratropical or mid-latitude cyclones don't have names, whereas tropical cyclones always get named. So it's called a hurricane if it's a tropical cyclone in the Atlantic and Eastern Pacific Oceans. This is after the Caribbean evil god of winds and destruction. It's called a typhoon if it is west of the international dateline and north of the equator. This is after the Chinese for scary wind or wind from four directions. And then it's given some other variation of the name cyclone if it's a tropical cyclone that is in the Pacific south of the equator or the Indian Ocean. So basically not one of these other two specific locations. Cyclone comes from Greek for coil of a snake. We classify tropical cyclones using the Saffir-Simpson scale. Which is going to use the highest 1 minute average wind speed in the storm. As the wind speed increases, the central atmospheric pressure will drop, but we're using that wind speed really to determine the category. So, remember I said that an EF5 is much higher wind speeds than a hurricane? The Category 5 hurricane, the biggest hurricane, its wind speeds are only 249 kilometers per hour. An EF5 tornado, it was 322 kilometers per hour. So yeah, tornadoes spin faster. But hurricanes have more things going on. So this is rated 1 to 5. When you hear someone say in a category 1, category 2, whatever. Category 5 is the most severe. A hurricane can move up and down. So they tend to be higher categories when they're out over the warm ocean water, and they will decrease as they approach land, which is a good thing. We want them to be lower categories because category 5 storms are nothing to sneer at. So this first sentence, no real damage to building structures. You have damage in any hurricane. You have massive winds, lots of water. You do have damage. You have flooding, whatnot. So this is okay. So let me just point out this sentence here. Hurricanes Irene of 1999 and Katrina of 2005 were Category 1 hurricanes when they made landfall in South Florida. Katrina at least gained speed when it went over the Gulf. But we have some, you still have major damage, no matter what. So Category 5s, which are the largest ones, Andrew of 92, Wilma of 2005. There have been other Category 5 since then. These are the big storms. So how do we name hurricanes? So extratropical cyclones are normally not given a name. Again, mid-latitude cyclones, they're not given a name. They may be identified by the region of formation. All tropical cyclones that form into depressions, storms, and hurricanes are given an individual name. This is standardized by the World Meteorological Organization, WMO. Once the maximum sustained wind speed exceeds 63 miles per hour, so that is a tropical storm, it gets a name. The name is assigned sequentially from a list of previously agreed upon names for the region of formation. So like the Atlantic Ocean has its list of names. So for the Atlantic Ocean, we have 6 lists of male and female names. Each list has 21 names, so we don't have a name for every single letter of the alphabet. These names come from English, French, and Spanish, and those lists will rotate. Exceptionally damaging storms are retired, so things like Katrina, Rita, Ivan, I'm pretty sure Sandy, these get retired. They're not going to be reused. Prior to 2021, if we exceeded those 21 lists, names on the list. So if we had more than 21 named storms, they would move to Greek letters. This happened in 2005 and in 2020. This is showing you that we are starting to have more storms. This is problematic because I remember in 2020, we had some big storms that had those Greek names. We got pretty far in the Greek alphabet. So what happens if you have a massive hurricane beta? The next time you have to go to that backup list, well, beta is no longer available. So the WMO established after the 2020 season a secondary list. So now if we exceed the first list, we move to a secondary list of names, of approved names, so that we don't have to worry about the potential of having to retire a Greek name. That's a very new thing. So how do we form a tropical cyclone? Large thunderstorm complexes that rotate around an area of low pressure that forms over warm tropical, subtropical ocean water is the key for what is going to develop into these hurricanes. So a hurricane is if the wind speeds are greater than 119 kilometers per hour. We have to have tremendous heat. The surface sea temperatures have to be about 26 degrees, which is about 80 degrees Fahrenheit. So this is only going to happen in these warmest parts of the ocean. This is why they're only in the tropics. So these will begin as a tropical disturbance. So this is a large area of unsettled weather and thunderstorms that will last for more than a day. We can also have low pressure troughs. So this low pressure trough is basically where we're going to have convergence on one side of the axis, on the eastern side of the axis, and divergence on the western side. We will start to have weak partial rotation forming due to Coriolis effect. So we're going to start to slowly pull these convergent lines together. So this can form from lines of convection, so squall lines. We can have upper level low pressure troughs that will start to form this convergence. We can have remnants of cold fronts. And one of the very common ones is easterly waves of converging and diverging winds. They're called easterly waves because they're coming from the east, so they're coming from Africa. That's what we're seeing here, is that we actually have these lines of easterly waves, and we start this rotation where we have convergence on one side and divergence on the other side, and then we start this rotation. And so you basically can see different storms forming in the kinks of each of these easterly waves. And so we do see this during hurricane season, that we're looking at the closest one, but there are 2 or 3 behind it developing that we're also looking at. So easterly waves form over Western Africa. They are moving from the east, which is why they're called easterlies. They are troughs of low pressure, extending north-south, but a couple thousand kilometers. They move westward with the trade winds at about 15 to 30 kilometers per hour. The kinks and the trade winds cause convergence east of the axis of low pressure, and then the air rises and our clouds form. West of the axis, the winds diverge and the skies clear. So that's what we're seeing here, is that we have the convergence and then the divergence where the skies are clearing. Tropical disturbance becomes a depression if the winds increase and spiral and start to form a low pressure center around the middle. So warm air will draw down from above, increasing the spin. If the winds exceed 63 kilometers per hour, we call this a tropical storm, and it gets a name. Once a tropical storm gets its name, it keeps that same name. It may go back down to a depression, it may go up to a hurricane, it may go through different stages of the hurricane. It will keep that same name no matter what. Our Category 1 is once we exceed 119 kilometers per hour, and then we go up from there. So will a depression become a storm, become a hurricane? We have to have favorable conditions. So we need warm ocean waters to a depth of 46 meters. This is deep water, okay? It's not just warm surface water, it has to be very deep. So this is one of those things that I'm going to talk about next week. We're seeing warmer temperatures in the ocean routinely. The oceans are warming up. This means that we have the ingredients for hurricanes more often. The atmosphere must be able to cool fast enough above that surface for cloud formation when we lift that moist air. So we have to have that cool, dry air above the warm, moist air to form clouds. Unlike with traditional thunderstorms, we do not want vertical wind shear. We do not want the winds moving stuff around. We only want this to start to spin thanks to the Coriolis effect. And that Coriolis effect has to be strong enough to start that spinning. So when we have a hurricane, they are big. They're 500 kilometers diameter on average. They can be bigger. Sandy was 1,800 kilometers. We have hurricane force winds limited to the interior, about 160 kilometers. Gale force winds are in the outer portion, so that's only about 50 kilometers per hour. The hurricane is made up of rain bands, which will be clouds that spiral around the hurricane that obviously have rain. There will be an eye wall, that is the innermost set of clouds. This is where we have our most intense winds, and that eye wall will constantly change. And the eye is the calm at the center of the storm. It can be between 5 and 60 kilometers, and it is calm. There's nothing going on there. You just have to get through the most intense winds to get there. So what happens is we have rising, warm, moist air spiraling upward around that eye wall. It condenses into clouds, which releases further heat, which helps drive the process faster. That latent heat will warm the area. This strengthens the convecting updrafts, which continues to pull more warm, moist air up into the cloud. That upward spiraling draws air from the eye, causing now dry air to sink within the eye. So basically we are pulling this spiraling and we are forming this low pressure where we're pulling stuff down through the eye, because remember we have low pressure at the center. The upward airflow out of the storm acts as exhaust jets. This allows additional warm moist air to be pulled in the lower parts of the storm. So these will keep going until they run out of that warm moist air. Once they lose that warm moist air, once they don't have that heat, they will dissipate or turn into a extratropical cyclone. So where do they go? The Coriolis effect will drive the direction they go. So in the northern hemisphere, they will deflect right. In the southern hemisphere, they will deflect left. That is what we are seeing here. These are tracks of storms. So these here are the ones that we mostly think about in the US. These are the ones in the Atlantic. So we can see that they follow this track due to the Coriolis. We do not have the most hurricanes. Nope, that's not us. Typhoons are more common than hurricanes. So they move at 19 to 27 kilometers per hour, so that's about 12 to 17 miles per hour. They typically are a 2-day event, so they can stall for short periods of time, including offshore. When they stall offshore, they're basically gathering up more energy. They can have a rapid increase in wind speed. This can throw off models and potentially catch people off guard. As they get closer to landfall, we tend to get better predictions of where they're going to go. Extratropical cyclones can be formed from tropical cyclones. So when a tropical cyclone encounters upper-level low-pressure troughs, or they weaken as they move over land or cooler water, they can convert to an extratropical cyclone. So when the hurricane hits the Gulf and then continues on north, it becomes a regular extratropical cyclone by the time it hits us. So we need a strong temperature gradient in the air near the surface and wind patterns in the jet stream to help this happen. So we're typically encountering the jet stream when this happens. So the strongest temperature gradients are going to be along fronts. So the jet streams curve or meander in flow. The cyclones develop where these jet streams bend, split, and diverge. So they will strengthen when they cross low temperature gradients. So this means they get stronger in like the plains. Anytime they hit a strong temperature gradient, they are going to weaken. So these will develop in westerly winds, extratropical cyclones I'm talking about now, not easterly, so they typically track west to east. I've already talked about extratropical cyclones quite a bit. So extratropical cyclones will start as low pressure center along a frontal boundary. So here we have the development of a extratropical cyclone. So it will start as a cold front in the southwest, and it will be warm. There will be a warm front to the east of it. So if we look at A, that's what we see. We have cold. Basically, we have a cold front. So we have cold air moving into warm air. We have cold polar easterly winds to the north and warm, moist westerly winds to the south. They will start to rotate. This will be a counterclockwise rotation of circular or counterclockwise circulation, the cold air will start to wedge beneath the warm air to the southeast. So that's what we're seeing starting here. The warm, moist air will start to rise on the southeast side. This will create what are called comma clouds. So that's what we're seeing here. This is a comma cloud here. The dry air aloft will feed that cyclone and it will sink behind the cold front, and this causes the dry slot. So here we see the comma in a drawing, and here's the dry slot. And this can actually lead to what's called an occluded front. So we see that in the middle on these two panels. So the cold air, or the cold front, wraps around the cyclone and it merges with the warm front, and so we trap some of that warm air aloft, and that's the occluded front. Once the cold air is completely dissipated, and once the cold air completely displaces the warm air, that we only have equal temperatures, that is when the storm will start to dissipate. What regions are at risk? So for tropical cyclones, anywhere with warm water. So coasts along the western Atlantic, coasts along the eastern Pacific, the western Pacific, the Indian Ocean, coastal areas with warm water offshore. Those are the areas in danger of tropical cyclones. So this graphic shows us where we have tropical cyclones. Not quite sure why we don't have a lot that hit South America. I'm assuming it has to do with we don't have winds that go in that direction. Extratropical cyclones are the mid-latitude cyclones. There's a larger area at risk than the tropicals. These happen in the interior of continents. Winter storms in the U.S., we see them along the Pacific coast. We also see nor'easters along the eastern coast, and we see snowstorms in the west. In the U.S. summer, we see severe storm and tornadoes in the central regions. So here's an enlarged image of these tracks of tropical cyclones. One of the impacts of tropical cyclones is storm surge. So this is a local rise of sea level resulting from water being pushed shoreward by the winds. This is not a wave. This can be up to 12 meters possible. This tends to be worse when there's a gradual shallowing of the water, so it's easier for the water to come up. There are two mechanisms that cause this. One is the wind is being pushed, the wind is pushing the water surface. So the stronger the winds, the more the water will rise, because the water will rise proportionally to the square of the wind speed. The larger the fetch, or the area over which the wind blows, the higher the water will get, because you have more water available. The other thing that can make the water rise is low atmospheric pressure will pull at the sea surface. So for each centimeter, or you have 1 centimeter of increase in water for each millibar drop in pressure. So typically we're going to see about 100 millibar drops in pressure. That's a meter of rising water. The coastline will influence the height of the storm surge. So we can have it in the coastline shape can actually cause resonance, so it will get higher. We can have waves that will basically just amplify each other. We can also have what are called overwash deposits. So this is material that gets eroded away from the beach and carried inland and left. We can also have channels when we remove that material back out. So here we have a couple of overwash deposits, and here we see a bridge that has been destroyed by storm surge. This video will show you some of the impacts.
Powerful winds aren't the only deadly force during a hurricane. The greatest threat to life actually comes from the water, in the form of storm surge. Storm surge is water from the ocean that is pushed toward the shore by the force of the winds swirling around the hurricane. This advancing surge combines with the normal tides and can increase the water level by 30 feet or more. Storm surge combined with waves can cause extensive damage. It can severely erode beaches and coastal highways. The pounding waves can take out boats and buildings. As the waters move inland, rivers and lakes may be affected. and add to the rising flood levels. While we can't prevent storm surge, we do have a system that can warn us of the incoming threat. As a hurricane develops over the open ocean, forecasters at the National Hurricane Center closely monitor its path to evaluate the risk of a coastal strike. They use a computer model called SLOSH to predict storm surge heights. The model depends critically on the hurricane's track, intensity, and size. SLOSH uses water depths, land elevations, and barriers to the flow of water to compute surges as they move inland. This data helps determine which areas may need to be evacuated. When a hurricane slams our coast, it's important to be aware of all the dangers. As a reminder, emergency managers want us to run from the water and hide from the wind. Don't take unnecessary risks during a storm. Conditions can change in the blink of an eye. Storm surge is a dangerous event during a hurricane, where furious winds are driving deadly flows of water from our seas to our shores.
So yeah, if you're in a hurricane, it's probably not a good time to go ride your bike along the beach. Probably not the best. Or take your dog for a walk on the beach. So here's some examples of washover channels. So we've eroded away much of this material. Here is a before and after image of storm surge. So this water is getting quite far inland. One of the other impacts of tropical cyclones are extremely high winds. So while I said that a hurricane is not as fast winds as a tornado, it's still pretty fast winds. So the strongest winds are going to be in the eye wall. The highest sustained wind recorded was 310 kilometers per hour, about 190 kilometers per hour. The winds tend to diminish as we reach landfall. It may transition to an extratropical cyclone and still maintain those high winds. We can also have tornadoes associated with hurricanes. One of the major effects of tropical cyclones are going to be heavy rains and flooding. The average hurricane produces 1 trillion gallons of rainwater each day. That's a lot of water. So you also get a lot of rainwater with cyclones of lower intensity as well. So even if it's just a tropical storm, you're having a lot of rain. The extreme rainfall in a short period of time leads to massive flooding. We also have storm surge that can lead to flooding. So the flooding can be impacted by the storm's speed, so how fast it hits, how much time it's had to develop. Changes in land elevation, so the more gradual sloping are going to be more impacted by flooding. Interactions with other weather systems, did the storm increase or decrease? And then the ground saturation prior to the storm. Is there a place for that water to go? Mitigation. 53% of the U.S. population is in coastal areas, more in other countries. This may be an old statistic, so it could be more than that now. So we have watches. That means a tropical cyclone it will strike within the next 36 hours, and warnings, which means landfall is within 24 hours. Many people ignore these. I don't understand it, but many people do. So forecasts and warnings and nowcasting use radar. We look for that spin. We have what are called hurricane hunters. So they actually go out and they fly into the storm and collect data. We have weather buoys in the open water that will tell us what the conditions are. We can use computer models that will predict the path and the amount of storm surge. And again, we can predict the storm surge height as well. I apologize if you can hear the dog toy going on in the background. The problem with these is that there are always going to be people that don't listen for whatever reason. They can't get out. They don't want to leave their home. They have someone who has a mobility issue. They have animals. There's always reasons why people stay, and it's dangerous to do that. Hurricanes and the future. Hurricanes are costing more and more. So here we have a chart looking at the decades and the cost of property damage. Part of it is that the coasts are more built up and we have more expensive property at the coast. The storms are also probably getting worse. We have an increased population along the coast, and I'll say it again, global temperatures are rising. That includes the sea temperatures, and hurricanes need that warm water to form. So I predict we're going to see a larger number of storms. They may not be strong storms, but we're going to see more storms. Looking back at some of these other weather related hazards, so I already mentioned these last week. Fog is when we have a cloud in contact with the ground. Fog is dangerous because of very low visibility. If you are driving in fog, do not put your high beams on. They will bounce back and reflect at you and blind yourself. So, fog lights are designed to aim low on the ground. So, it is better if you don't have fog lights, just maintain using your regular headlights. Fog can form daily when warm air rises from the ground and intersects the cool air from the night before. Drought is an extended period of unusually low precipitation. It will produce shortages in water, which can lead to problems with the food supply. It doesn't just impact people. Our country experienced a decade-long drought in the plains in the early part of the 20th century called the Dust Bowl. We also can have windstorms. This is basically a mid-latitude cyclone that doesn't have rain. This happens a lot in mountainous areas. If those windstorms pick up sediment, they can be good dust storms. So dust storm is a strong windstorm with suspended sediment in it. This image is from Black Sunday, which was one of the extreme dust storms during the Dust Bowl. These things will reduce visibility. We also have biological hazards because what is the dust? Does it have spores? Does it have pollen? Is there other dangerous material in there? Plus, breathing dust isn't good. And that dust will stay in the atmosphere for a long time because it's very fine grained. If the sediment is sand, that is called a sandstorm. This tends to happen more in deserts. Sand is larger than dust and fine particulates, so it will be closer to the ground. So it's normally only a few meters high and it bounces along, but it's much more abrading because it's grittier. So we use sand in sandblasting. The natural wind can do the same thing. Hot weather can also be a problem. So this is called a heat wave. So this is a prolonged period of extreme heat. It's longer and hotter than normal. Sorry, I'm having to stare down with my dog who has brought her toy in here to now make obscene noises in here. Okay, she's ashamed of herself. So a heat wave is going to be both hotter and longer than normal. This tends to impact areas that aren't used to the heat, accustomed to the heat, worse than areas where people are accustomed to the heat. It is going to be worse on people that are susceptible, so people that are very young. When I say very young, I mean like babies. People that are very old, homeless, so they're exposed, ill, have some kind of underlying condition. This is true of most weather hazards. Heat waves are going to be associated with high pressure ridges. So the hotter things are associated with high pressure. The cold storms are associated with low pressure. You can either have a dry or a humid heat. This is going to be determined by heat index. So heat index is how your body perceives temperature. So similar to wind chill, which is how the temperature you feel due to the amount of wind, heat index is the temperature you feel due to the humidity. So air temperature is the actual temperature. Relative humidity will make the air temperature feel worse. So if we have any relative humidity, the air temperature feels hotter than it actually is. And the higher the amount of humidity, the worse this is. So if we look at 85% relative humidity, which is relatively high, we have 135 degrees heat index at 94 degree temperature. So we feel that same temperature at higher temperatures if we have lower humidity. So it's 136 heat index at 110 if we only have 40% relative humidity. So if we look at this 94 mark, let's look at the 100 mark. Okay. So if we have a 100 degree air temperature, it feels like 136 degrees to your body if there's 65% relative humidity, which isn't terribly high for a humid region. The colors on here are indicating the dangers to people, so these darker oranges are obviously more dangerous. Humans and weather. Agricultural processes or practices increase erosion and can cause dust storms. This was shown to happen during the Dust Bowl. We also periodically allow bad building practices. So we have tornadoes or trailers in tornado impacted areas. People build regular beach condos instead of hurricane resistant beach condos, things like that. We do also see what's called the urban heat island effect. So you can observe this every summer if you watch the weather and look at the map of temperatures. The highest temperatures will always be in the city, and we will have lower temperatures in the suburbs. And this happens in every city. The large areas of pavement will increase the temperature in urban areas. And we are seeing global temperatures are increasing year to year. And this is causing changes in our climate, which I will talk more about next week. So we have weather, we're actually pretty good. We've gotten pretty good at weather. Forecasting using Doppler radar, it's pretty good. Nowcasting, which is where we're looking at the immediate case, is even better. So this is where we have our news anchors on 24/7 during major events. Things like tornadoes tend to be fairly quick to develop, but typically we have seen the conditions developing, so we have put forth watches and warnings. A watch will turn into a warning. So if I have the ingredients for a taco, that's a taco watch. If I have the ingredients for a tornado, that's a tornado watch. If I've put together my taco and I can see it, that's a taco warning. If someone has spotted a tornado, that's a tornado warning. Or we see the rotation, that's a tornado warning. So warnings are the ones you don't want to ignore. Mitigation is going to depend on trying to minimize many of these impacts. So we're looking at building codes. So this is what are you allowed to do in these certain areas. FEMA, the Federal Emergency Management Agency, has guidelines. They also tend to come out after disasters to help. We always want to make sure our critical facilities will operate during severe events. So if there's a way to make sure we don't lose power, that we don't lose communication. Warning systems are very important. So things like tornado sirens, tsunami warning sirens, but that's not from weather. So warning systems, they come out, you get warnings on your phone for severe weather now. So these things are important. It's also important the public understands what they mean and knows what to do. And then insurance is kind of the last ditch effort. Most weather related things, aside from seasonal flooding, will be covered by basic insurance. It's important to be prepared. So this is to know what to do in severe weather. So when you get that alert on your phone, what do you do? Knowing your local weather patterns so you can recognize this if you're out and about. What does it mean when you see a green sky? That green sky means that a tornado is coming and you go and get undercover. Where to go? Where's the best place to go in the case of a tornado? Having supplies ready. So when I used to drive back between St. Louis and Philadelphia for Christmas break, I would always have a suitcase full of winter gear in my car. It's still in my car actually, as well as a shovel and some other supplies just in case, because I didn't know what I was going to necessarily encounter at the higher elevations as I crossed the mountains. You want to dress appropriately. So for example, if it's very cold out, you want to be prepared for it. If it's very hot out, be prepared for it. Also know your own limits. So I personally know I'm very susceptible to overheating. So when it's very hot, I'm careful about what I do so that I don't overheat. Don't go outside in severe weather unless it's absolutely necessary. Do you really need to go to the grocery store during that blizzard? Probably not. And adjust travel as necessary, which is a little bit more challenging when you're looking at like air travel and stuff. But it is important to recognize that you have to make smart decisions. So I am now going to show the pre-lab video. So this is Earth-Sun relationships. This is about our seasons mostly. So a little bit about what we talked about last week. I probably should flip these, but it's also a bit helpful to have done the lab last week before we're talking about this material.
Hello students, welcome back for another pre-lab video. This is Callan Bentley. This week in lab, we're going to take a look at the various relationships between the Earth and the Sun. So one thing that we want to pay attention to is where the Sun is in the sky and how long it stays there. So in short, we're going to be looking at intensity versus duration. You probably noticed that both intensity and duration of sunshine vary throughout the year. During the summer, the sun is higher overhead and the days last longer, and during the winter, the sun is at a lower position in the sky and the days are shorter. Let's examine these in turn. First off is the issue of intensity, which is defined by the sun's position relative to the ground. So you can do a little simulation this week in lab where you take a look at equal-sized sunbeams leaving the sun and then pay attention to how much of Earth's surface they spread out over. The more surface that they spread out over, the less intense the sun is, the lower the angle of the sun in the sky. You can take a look at this on a planetary perspective, thinking about three slices of the Earth's surface. One wedge here marked by a 30-degree angle with Earth's interior, resulting in 30 degrees of arc of Earth's surface, another one here, and another one here. So what we want to do is we want to take a look at the angle of incoming sun rays relative to Earth's surface. And you can measure this with a protractor. The key question here is, when we divide that quarter of the planet up into thirds, what percentage of the incoming sunlight does each third get? You can probably just visually estimate here that the one closest to the equator is going to get the greatest amount, and the one closer to the pole is going to get the least amount. The angle of incoming sunlight, of course, doesn't stay constant over time, but it changes over the course of the year. So during the northern hemisphere winter, the southern hemisphere is more directly illuminated by the sun, and so it'd be the austral summer and the boreal winter. So the angle of the sun coming in is going to be at a lower angle for, say, North America at that time of year. During the equinox, whether it's fall or spring, this is when the sun's incoming rays are directly perpendicular to Earth's surface at the equator, and the sun is directly overhead. During the northern hemisphere summer and the austral winter, we see that the incoming sun rays are overhead or more close to overhead in the northern hemisphere than they are in the southern hemisphere. This table shows this data in numerical form, where you're looking at the different degrees of latitude. This could be north or south, so you could think of it in terms of the northern hemisphere, so think of it as degrees north, and then the summer solstice, the winter solstice, and the equinoxes. You can see here at the equator, during the summer solstice and at the winter solstice and during the equinoxes, the day is going to be 12 hours long. But as you move away from the equator toward the poles, you see that there is an increasing amount of sunlight during the summer and a decreasing amount of sunlight during the winter. And so once you're north of the Arctic Circle there at 66.5 degrees, you can see that in the summer you basically have 24-hour sunlight, and in the winter you have no sunlight at all. Notice that everywhere, no matter what latitude you're at, during the equinoxes, the day's exactly the same length, 12 hours. This graph is a special graph called the analemma, and basically what it shows is the changing position of the sun in the sky over the course of the year. If you were to take successive photographs of the sun at, say, exactly 12 noon every few days over the course of the year, the position of the sun in the sky would describe the same shape, the analemma. You can also view it as a graph of the latitude of the vertical noon sun versus how far it's offset relative to longitude, which basically means that the solar clock is either a little fast or a little slow, and that changes systematically over the course of the year as well. You'll be able to use this graph to estimate the latitude that the sun would be vertically overhead at noon on any given day of the year. Here's another exercise that you'll look at that has to do with sun-Earth relationships. The angle of incoming sun rays is actually exactly proportional to the latitude. So let's take a look at this example down here. If we are in December near the solstice, we're at 23.5 degrees south latitude. That means that the sun's going to be directly overhead. So that's the situation right here. There's a 90-degree angle between Earth's surface and the incoming sun rays at 23.5 degrees south. We can actually quite easily calculate what the angle of the incoming sun rays are anywhere on the planet based on that single piece of information. So say, for instance, we're interested in looking at this location, 40 degrees north latitude. What's the angle of the incoming sun rays at noon on that same day, that winter solstice? 40 degrees north is 63.5 degrees away from 23.5 degrees south. So you go 23.5 degrees north and you're at the equator, and then you end up going another 40 degrees north and you're at 40 degrees north. 40 plus 23.5 is 63.5. Then you go ahead and you subtract 63.5 from 90 degrees. The result of that calculation is 26.5 degrees. That 26.5 degrees is the angle of incoming sunlight at noon at that latitude. Pretty easy, right? You'll also be asked to take a look at systematic variations in the amount of solar radiation that is received at different latitudes over the course of the year. You're going to be given this table which has data for 3 different latitudes: 90 degrees north, which is the North Pole; 40 degrees north, which is about the latitude of, say, Philadelphia; and the equator. And then you'll have 4 time series of data: March, June, September, and December for each location. You're going to be asked to plot that on a graph and then explain why the variations that you see occur in the way that they do. So what explains the rise and fall of solar radiation at any given latitude over the course of the year, and in particular the magnitude of that rise and fall? We live on the Earth, we rely on the sun. Let's spend a little bit of time this week looking at the relationship between those two important bodies in our solar system. Good luck.
So let me just point out that he was saying 40 degrees north is about the location of Philadelphia. 40 degrees north is also about the latitude of St. Louis. So that's our latitude here. So when we're doing that exercise, you can basically think about it as being where we're at. So that is all I have to talk about weather. Again, I'm not a meteorologist. I'm not an expert in this, so please do read your chapter. It is fascinating, and I truly admire people that decide that this is what they want to do, because when they get it wrong, they get in so much trouble. So I think it's important to understand some of the basics so that the next time you do watch a weather report, you will be able to understand it a little bit better. So that is it for this recorded lecture.